In this podcast, we will explore the core characteristics of science and how those characteristics can be modeled in the classroom. Science assumes that the natural world can be understood by gathering evidence. Also, science attempts to explain the natural world, and these explanations are tested using evidence. So, magic, gremlins, or supernatural beings are not needed to explain the natural world. If we look at science inquiry, or how we can model science in the classroom, there are a few things that are kind of essential to this. According to the National Research Council, these features are: 1. The learner engages in scientifically oriented questions. 2. The learner gives priority to evidence. 3. Learner formulates explanations from evidence. 4. The learner connects those explanations to scientific knowledge. And 5. The learner communicates and justifies those explanations. So what isn't in these descriptions that you'd expect to see? You might notice that the word experimentation is nowhere to be found. Scientists use many different approaches to identify evidence and test explanations. Experimentation is only one of these. We need to make sure that our classrooms reflect the diversity of science inquiry. Now if you look at these, what do you notice? The word explanations and evidence are used quite often. The central concept, or the central core of science inquiry, is the fact that our students should be creating evidence-based explanations. These explanations should be supported by evidence, and reasoning should be used to connect the evidence to those explanations. Let's take an example of the cane toad. So cane toads are large poisonous toads that have a voracious appetite. Their primary mode of identifying prey is through seeing motion, but they can also use smell. Cane toads prefer insects but will eat small rodents, amphibians, and even human rubbish.
The cane toad like to going underneath lights. The lights reflect the moths, the insects. And this way he goes underneath it and swallows them up. His reaction is the same thing, like a vacuum cleaner. If he sees something drop off, he goes and pick it up and swallow it in like a vacuum cleaner sucks it into his body.
Gut content analysis has shown that it'll eat virtually any living thing that's small enough to get in its mouth, from frogs to small birds to caterpillars to insects, crabs, all sorts of things. In fact, one researcher showed that the toad will even try and eat ping pong balls as they bounce past the front of them. So the general selection of food for a cane toad is if it moves, or even if it doesn't move, if it can be fitted into its mouth, then it will attempt to eat it.
Researchers in Sydney, Australia observed that cane toads exhibited cannibalistic tendencies. After initial observations in the field, they set up a controlled laboratory investigation and found that adult male cane toads would wiggle their middle toe on their hind foot. When they did this, young cane toads would approach the adults and be eaten. Now let's say that these scientists only reported the facts. They would simply restate their observations. Adult cane toads wiggle their middle toes, which appear to cause young toads to approach them. When they are close enough, the adults eat young. Although accurate, it really doesn't give us much understanding of the mechanisms at work here. However, scientists go beyond just reporting the facts. They develop explanations for those facts. The lead researcher stated this explanation: the toe waving seems to be beautifully designed to arouse the feeding responses of small cane toads. They presumably think it looks like a small insect. Hungry young toads approach the wiggling toe, thinking that it is food. When they get close enough, the adults eat them. This reasoned explanation fits well with evidence and with what students already know about the cane toad's diet. We need to do this in the classroom, push our students beyond just data reporting, and have them develop evidence-based explanations. These explanations, in the science community, these explanations, once they're developed, go out to the community for analysis, feedback, and rigorous peer review. This will either support or add additional questions and strengthen or weaken those explanations. As explanations grow and are supported by more and more evidence, they become more robust and become more accepted by that scientific community. So let's take a look at what's happening in the classroom. There's quite a bit of research that shows that our focus in the science classroom is not on creating scientific explanations based on evidence. Research done by Kuhn and Newton, Driver, and Osborne show that explanations are rarely part of the science classroom practice. According to Sandoval and Reiser, students have difficulty using appropriate evidence, and Bell and Lin found that they rarely include backing for why they choose their evidence. Other researchers find that during classroom discourse, discussions tend to be dominated by claims with little backing to support their claims. Too often, we end with just reporting facts and not building explanations. When teachers first start thinking about science inquiry, the one thing that often comes to mind is what do we do about standards? How are we supposed to cover all of our material, do science inquiry, still prepare students for standardized testing, and just basically get everything done? It's a huge concern. A few things that we should note is, first of all, the AAAS Benchmarks for Science Literacy, which is really the foundational document for all of the national and state science standards documents, has quite a bit about science inquiry and using explanations. Here are a few excerpts. At the kindergarten, first, second grade level, the benchmarks state, people are more likely to believe your ideas if you had reasons for them. In third through fifth grade, the benchmark states, seek better reasons for believing something than everybody knows that, or I just know, and discount such reasons when they are given by others. As we get into middle school, students are expected to notice and criticize the reasoning and arguments in which fact and opinion are intermingled, or the conclusions do not follow logically from the evidence given. And then in high school, we should insist that the critical assumptions behind any line of reasoning be made explicit so that the validity of the position taken, whether one's own or that of others, can be judged. So it's very clear in the standards that we need to be focusing on students building evidence-based explanations for scientific concepts. There's quite a bit of educational research that also shows that science inquiry and a focus on evidence-based explanations work. One of the most recent is a study conducted by researchers from the University of Michigan. They followed two cohorts of 7th and 8th graders that participated in a science inquiry project. They compared with them with the remainder of the district population. This was done as a large-scale study with over 6,000 students involved. Using results from high-stakes standardized testing in science, both the initial and scaled-up cohorts showed increase in science content understanding and process skills over their peers, and significantly higher pass rates on the statewide test. The relative gains occur up to a year and a half after participation in the science inquiry-based curriculum. The effect of participation in units at different grade levels is independent and cumulative, with higher levels of participation associated with similarly high achievement scores. Examination of results by gender reveals that curriculum efforts succeed in reducing the gender gap in achievement experienced by urban African American boys. There's also additional research that shows that science inquiry approaches reduce achievement gaps between all minority populations. So as we think about teaching, we need to keep science inquiry at our core. It needs to be the core pedagogical philosophy that we approach instructional practice. Science inquiry needs to focus on students developing scientifically oriented questions or answering scientifically oriented questions, focusing on building explanations from evidence and connecting that evidence to their explanations through reasoning.